So this week we have discussed about many of the lower scaling method. One of the important things we have discussed while discussing electron correlation method is that this methods gives very good answer for energy as well as properties only when we use a large basis set. Generally, a double zeta size basis set used with correlation method actually has no meaning because it does not give you the required accuracy. Now, one problem with the electron correlation method is that they scale very steeply with respect to the system size. So, even if you use lower scaling approximation, be it Ri, cos x or localized orbital natural orbital based approximation, your reduction in the computation cost may be significant using this approximation, but still it is not practical often to do a quadruple zeta basis set calculation or maybe go beyond quadruple zeta, maybe pentapole zeta calculation. So, one alternative approach can be that you take a systematic set of basis functions and try to fit a functional form how this energy depend upon the size of the basis set, and then using that functional form you extrapolate it to the complete basis set limit. So, in the complete basis set limit, this is often called CBS extrapolation scheme. In the ab initio calculation, the wave function of a system is represented as a linear combination of atom centered basis sets. And to get a good approximation to the exact energy of the system, what you need to do, you need to perform calculations at least at the complete basis set limit. So, the basis set should be as high as possible. And the second thing is that you need to have a good description of the electron correlation energy. Now, what is a good description of the correlation energy? There is no clear answer to it. In ideal case, full CI is the of course best solution, but full CI you cannot really do on anything beyond a diatomic molecule in a very small basis set. So, for all practical purposes you need to take approximation. Now, which approximation depends upon the system size, what kind of accuracies you are looking at it, which I will tell as horses for the courses. Depending upon what kind of accuracies you need, that kind of electronic structure method you are going to use. Provided you can use a particular type of electronic structure method, doing calculation at the CBS limit means an infinite number of basis functions to represent the wave function, but it is not possible to do. So, basis sets. So, what you do, as I discussed, that you will find out how the energy or the particular property depends upon a particular kind of basis functions, how it depends upon its size. And so, the basis set used for CBS calculations are developed in such a way that they converge to the basis set limit as the number of basis functions goes to increase. And there are many CBS extrapolation scheme possible. One of the most popular one uses the correlation consistent basis set. These basis sets are used in such a way. These are developed by Dunning and co-workers, and we have discussed the acronym CCPV NZ, where n can be DT cube 5 6 etc. This kind of basis sets, the Dunning basis set has two kind of things. First of all, they are developed to extrapolate the correlation energy to the complete basis set limit. So, you can do calculation systematically DTQ. Secondly, these basis sets are designed to perform calculation with the frozen core approximation. That means, if you freeze the core, your number of electron will be less, so your computation timing will be much less. Now, what happens is this CBS extrapolation procedure is that you extrapolate both the Hartree-Fock and the electron correlation method. Now, Hartree-Fock and electron correlation method, we have discussed that their basis set convergence is different. Generally, Hartree-Fock converges quickly with respect to the basis set size than what is observed for the electron correlation method. So, for Hartree-Fock method, what you do is that you extrapolate it with respect to the size of the basis set by using this kind of a formula, where E SCFX is the SCF energy at a particular basis set, E infinity SCF is the SCF energy at the complete basis set limit, and this is the formula where A and alpha is two unknowns basically, and it has an exponential dependence. So, what is done in the case of SCF is that you calculate at different basis sets and then you put it into the extrapolated formula, where you can find out the A and the alpha coefficients are predetermined. Similarly, for the correlation, one uses a different formula which is called an inverse cubic formula. So, you have the correlation energy at two different basis set, and then you using this formula you go to this infinite basis set for the correlation energy. So, you separately extrapolate SCF and correlation part and then add it together to get the total extrapolated energy. So, x and y both in this case was correlation in the cardinal numbers for the correlation energy, and the exponent beta depends upon the basis set and for which the xy is employed. So, these values of the alpha and betas are predetermined, and you can find out the reference. Just before going into that, it's necessary to tell that these are not the only way of extrapolating basis set formulas. There are multiple ways of extrapolating complete basis set limit, but these two are generally most popular. So, this alpha and betas are predetermined, and you can find out from this paper for different families of basis set. You can find out different values of alphas and betas. So, you can have CCPB, NZ, PC, DEF2, ANO, and your basis set cardinal number can be also different. So, you can extrapolate from double zeta to triple zeta, or you can extrapolate to triple zeta to quadruple zeta. There are formulas where it uses a 3-point formula, double zeta, triple zeta, quadruple zeta to extrapolate, but 2-point extrapolated formulas are generally optimal between computation cost and accuracy. Now, question is that which of the basis set extrapolation formulas you should use? Should you use the double zeta and triple zeta, or triple zeta and quadruple zeta? Of course, in terms of computation cost, it is preferable to use double zeta and triple zeta. Just to see how much error it gives, here is the error with respect to the different kind of basis set, and the complete basis set limits were calculated. I think for the Hartree-Fock it was calculated using augmented CCPV 5Z, and for the correlation part it was calculated using some 5 zeta kind of basis set and some R12 or explicit correlated method. So, with respect to the complete basis set limit, where you can actually converge your energy increasing the basis set to such an extent that even if you include more number of basis functions, your energy will not change, that you take as a complete basis set limit. And this is what you get by extrapolating using these formulas: 2/3 extrapolation, 3/4 extrapolation. So, here are the parameters for each kind of basis set, and its mean unsigned error. If you see, this is the energy at the error at the Hartree-Fock, error at the correlation, this is the total error. First thing to notice is that the error in the Hartree-Fock due to basis set extrapolation is generally smaller than what you see with respect to the error in correlation, because correlation energy converges much more slowly than the Hartree-Fock. And here you see the same for 3/4 extrapolation, where your error with respect to the complete basis set limit is given. In this case also the error in correlation is higher than the error in the Hartree-Fock thing, because correlation converges slowly. But one important thing to notice is that if you do the 3/4 extrapolation, the total error in the total energy is much smaller than what you see than 2/3 extrapolation. So, 3/4 extrapolation, if you can afford, it is always preferred to do 3/4 extrapolation using the 3/4 extrapolation scheme. Now, we are going to show some example how to perform these calculations. So, let us again go back to our favorite example of CH2, but before that let us see what are the keywords. So, in the case of ORCA, there are two formulas if you want to 2-point extrapolation. So, the formula is that you have to use the keyword extrapolate. X and Y are the cardinal number, and basis is the what kind of basis you use: CC, augmented CC, CC core, ANO, augmented ANO, DEF2, like this. So, here you are going to give the number, or you can use the 3-point extrapolation formula, where you extrapolation n is the number of energy point used, and you give the basis set. So, if you give a 3-point formula, of course, it will start from double zeta, triple zeta and quadruple zeta. Similar, if you give 2, it will start with double zeta, triple zeta. So, there are two alternative ways depending upon what you want to do. You can use any of the formula. More details are there in the ORCA manual. We are going to use the first formula, and we are going to go back to our favorite example of CH2 triplet singlet gap, and we are going to extrapolate. Previously, we have shown how to perform DLPNO's CCSD parenthesis T calculation with CCP QZ basis set. So, today we are not going to do the QZ basis set calculation, but perform double zeta and triple zeta and extrapolate it and see how the values look like. We are also going to perform extrapolation with DEF2 kind of basis set, and we will see how the numbers actually look like at the complete basis set limit. So let us do the calculation. This is the CH2 triplet DLP input file. I make another folder, week 5, inside it's CBS, DLP CBS. I can write everything small dot INP. So this is the command. It's 2,3. My basis set is CC. These basis sets are not required. And in the previous case, we have shown that it actually requires more energy, so we keep the max score. We save it. This is my input file ch2t dlpno cbs.out, and I know this will not run. So first thing is that it says all non-ASCII type character from your input file. Okay, what is non-ASCII type character I have? I copy pasted it. So sometime while copy pasting, what happens is that there are characters which are non-ASCII gets copied, which we may not able to see. I hope this will solve the problem. This is now another error in this case. Now I have to see the output file to see what is the error. So it says that your auxiliary basis sets are not defined. You can define the auxiliary basis set one by one, but what I will do here as an easy way is to use the keyword auto-aux. So it will generate an auxiliary basis set automatically. Now this calculation should run. I intentionally did not put the auto-aux, so just to remind you that if you do this extrapolation, complete basis set extrapolation, either you have to specify the auxiliary basis set yourself or just use the auto-aux option. This calculation can take some time. So in the meantime, why don't we prepare the input file for the singlet state? Week 4, CH2 SDLPN, this is triplet, this is the input file. I do not need this part, I just need auto-aux. Go to week 5, CBS. So my calculation is done. Yep. Open the terminal again. Vodka CH2S. No, I have to go to week 5. CBS. So let's see what is the triplet output file, how it looks like. Somehow this job is not complete, so we have to rerun it again. Let us first finish the singlet job and then we can go for the triplet job. Let's say it's done. Here you see the extrapolated energy. So this is the extrapolated SCF energy, this is the extrapolated correlation energy, and this is the total extrapolated energy. So let us copy it for singlet, go to my Excel file. You see that the extrapolated energy is CBS DLPNO CC. There. Now see the triplet one. If I see the triplet output file, it was not complete last time. I think we have to run it again. There's a problem. I think we can just need to delete the temp files. So sometime what happens if you run the same job more than one time in the same folder, the temporary files actually gets accumulated, and when you run it next time, it can lead to you errors. So one need to be careful while doing that. So triplet generally takes some more time because in the case of singlet, your number of orbitals is half of the number of electron, which is not the case of triplet. You are using an unrestricted reference, so it can take some time more time than the singlet. The calculation is still going on. It's some error has happened for which the calculation has crashed. This is singlet. I need to open the triplet output file to see what has happened. Again, some problem with the guess file. So we need to not only delete temporary file, we need to delete all the GBW file as well as the guess files. This should run. Calculation is done. So now let us open the file. ch2 dlpiano. This is the output file, and if we go here, again you will see the 2-3 extrapolation scheme, how the SCF energy is extrapolated, how much is the correlation energy is extrapolated, and this is the CBS total energy. I think I have not put the minus sign. Copy. So now see, this is the singlet triplet gap. So I have done with double zeta calculation and triple zeta calculation. If you would have done double zeta and only double zeta or triple zeta, and double zeta you get 10.33. But by doing the complete basis set extrapolation, you can actually get very good agreement with the quadruple zeta. Actually, the agreement with the experiment even improves when you go to the CBS limit. So this is the advantage of doing the CBS limit. I will give you one problem for you to practice. So perform the same kind of CBS extrapolation limit now with def2 kind of basis set and see how much is the computation timing, and has changed. Def2 basis set will get slightly smaller number of basis functions, and your accuracy you can see how much is your accuracy is affected by using a smaller basis set. So you can try this one, and then one can check the results.